Hi, I'm Joe Tan. I'm a final year PhD student at the ISVR in Southampton, and I'll be presenting today a wave-based active control system for non-reciprocal sound transmission and absorption. This work was done with Dr. Jordan Cheer and Professor Stephen Daly. The reciprocity is a fundamental property that describes symmetry in sound transmission between 2 points. So say you've got an acoustic source, an observer. The sound transmission in this case is equal to the sound transmission when the two interchange locations. However, this property is not desirable in certain applications, which has led to significant interest in developing non-reciprocal acoustic devices. Typically, non-reciprocal sound transmission is achieved by introducing non-linearities or breaking symmetry using resonant cavities or fluid momentum biasing. An example of this is the one on the left, where you can see a piezo patch placed in the center between two household resonators that are tuned to different frequencies. This creates a non-linear, non-reciprocal acoustic device, whilst the one in the center is an acoustic circulator, which creates momentum biasing. By using a fan placed in the center, and acoustic propagation can only propagate in one direction. Similar behavior can be achieved by using three household resonators, which are tuned to different frequencies. To further explain this concept, I'll give another example of one-way transmission. In this case, you've got a house as a window with privacy glass. So the person on the inside of the house can look out through the window and they can see the exterior field. Whilst anyone passing by looking through the window, the light is reflected back and they can't see what's inside the house. This gives the ability to see without being seen. Same with non-reciprocal acoustic devices. You have an exterior and interior field separated by a non-reciprocal acoustic device. The exterior field can propagate through the non-reciprocal acoustic device and is perfectly transmitted, whilst the interior field is blocked or reflected. It gives you the ability to hear without being heard. Non-reciprocal acoustic devices based on resonant cavities typically only achieve non-reciprocal behavior over a narrow frequency range. This is because they're highly reliant on the resonant frequency of the passive resonators to achieve this behavior. Although broadband non-reciprocal behavior has been achieved by using non-linear acoustic devices, these typically have limitations as well, such as signal distortions, and the directivity of the non-reciprocal behavior is favorable to one side and it cannot be reversed. Therefore, we want to investigate how broadband non-reciprocal transmission and absorption can be achieved using active control. This active control system has the ability to control the transmitted and reflected waves individually, and the advantage of this active control system is that it's fully adaptable. So this is a system that we'll use to demonstrate how non-reciprocal behavior can be achieved using active control. This is a one-dimensional duct. So as you can see here, you've got an ICO termination and primary source at each end of the duct. An active control unit placed in the center, with two pressure microphones either side. The positive and negative traveling waves in the upstream and downstream sections of the duct are also shown here, and these are labeled from A to D. Throughout this presentation, when I refer to a positive traveling wave, this is going from left to right, whereas a negative traveling wave is going from right to left. There's two different active control strategies that will be considered. This is a single point monopole control source that's driven to minimize the transmitted wave C, where a pair of point monopole control sources that are driven to minimize the reflected and transmitted waves C and B. In order to control the transmitted and reflected wave components separately, these need to be separated using a wave separation method. And in this case, we've used the integration method. It uses two closely spaced pressure sensors in the duct. And this, you calculate the average pressure and the particle velocity at the midpoint between these two sensors. using this equation here, where you do the average pressure, and the particle velocity is calculated from the pressure gradient. Using the pressure and particle velocity at the midpoint, we're able to calculate the positive and negative propagating waves in the upstream and downstream sections of the duct using the two equations here. Here I'm going to briefly explain the two proposed active control systems for non-reciprocal acoustics. For conciseness, I've not included the derivations of these equations, however these can be found in the paper. In both the active control systems, they use a feed-forward FX LMS algorithm, which is used to control the wave components. The error signal in the single point monopole case is the transmitted wave C, and the error signal in the pair of monopole case is the transmitted wave C and the reflected wave B components. The reference signal in both cases is the positive travelling wave, which is shown by coefficient A. On the left here, you can see the plot diagram for non-reciprocal sound transmission. So here you can see the measured pressure from each sensor, and this goes to the wave decomposition method, which was shown in the previous slide, in order to calculate the positive and negative travelling waves in the upstream and downstream sections of the duct. And then we take the positive travelling wave A and the transmitted wave C, and this goes into the transmitted wave LMS algorithm, which calculates the optimal control source voltage in order to drive this single monopole control source to minimize the transmitted wave. Similarly, for the non-reciprocal absorption case, the pressure again is measured at each sensor, and this goes to the wave decomposition method to calculate positive and negative travelling waves in the upstream and downstream sections of the duct. However, in this case, you have two single-channel LMS algorithms, where one is given to calculates the optimal control source voltage for the downstream control source to minimize the transmitted wave, and the other one is a reflected wave LMS algorithm, which is used to drive the upstream facing control source to minimize the reflected wave B. Here I'm going to present the simulation results when implementing the two proposed active control systems shown in the previous slide. The performance of the active control systems have been evaluated in terms of transmitted energy, which is shown by the blue line in all these plots, the reflected energy, which is shown by the red line in all these plots, and the absorbed energy, which is shown by the black line in all these plots. The performance of the proposed active control system is evaluated in two scenarios, when the active control system is subject to a positive travelling incident wave and a negative travelling incident wave. Each of the plots will show, as mentioned, the energy of the transmission, reflection, and absorption against frequency. So in the non-reciprocal sound transmission case, so the single monopole control source is driven to minimize the transmitted wave. When it's subject to a positive travelling incident wave, here you can see the transmitted wave is minimized, which is the objective of this controller. However, there's no constraint on the upstream sections of the duct, hence why you get perfect reflection with zero absorption. However, when the same control strategy is subject to a negative travelling incident wave, this achieves perfect transmission with zero reflection and absorption. This is because the reference signal is the positive travelling wave, incident wave, which in this case, when subject to a negative travelling wave, this A wave is now the downstream reflection, which is zero in this case, and therefore the feed-forward control has no time advance information, and it cannot control, or it does not control, the transmitted wave. Here again, for the two plots on the bottom, this shows the non-reciprocal sound absorption. So when subject to positive travelling incident wave, the parent monopole control sources minimizes transmitted reflected waves, which leads to perfect absorption. However, when this same active control strategy is subject to a negative traveling wave, this achieves perfect transmission with zero reflection and zero absorption. Again, this is because, similar to the single monopole case, this is because there is no time advance information for feed-forward control, and so it doesn't minimize the transmitted and reflected waves. Both of these plots show that non-reciprocal sound transmission and absorption can be achieved by using active control. The results presented on the previous slide show that we're able to achieve broadband non-reciprocal sound transmission and absorption using active control. So now I'm going to briefly explain the applications for non-reciprocal acoustic devices. As I mentioned previously, you can use it for active noise control, where you want to detect an exterior sound field whilst not being detected, so the interior noise is blocked or reflected. Another application is for full duplex communication, where you're able to transmit and receive signals on the same transducer. And another application is for invisible sensors, where you're supposed to detect a sound field whilst any unwanted noise is blocked in the other direction and does not contaminate the sound field. So the conclusions of this presentation, we show that an active control system has the ability to control transmitted and reflected wave components separately to achieve broadband non-reciprocal sound transmission and absorption in a one-dimensional waveguide. And this control system is also fully adaptable. For future work, I'd like to investigate whether non-reciprocal sound transmission and absorption can be achieved in an online system, and investigate whether non-reciprocal control can be achieved in a 2D and 3D environment. Thank you for listening. Happy to take any questions.